When a matrix has an inverse, we can use that inverse to solve any equation that that matrix participates in just by multiplying by that inverse to cancel the original matrix. Let's take a look at how it works. To use invertibility to solve a linear equation, ax equals b, where A is a matrix and x and b are vectors, we first need to know that there's a chance that the matrix has an inverse at all. And in order to have an inverse, a matrix must first of all be a square matrix, because we're going to need it to have a pivot in every single row and every single column. Not every square matrix has this property, but every non-square matrix does not have this property. So if you have a non-square matrix A, you won't be able to use this approach to solve the equation, and you should choose another, such as augmenting the matrix and row reducing. In our example, we have a square matrix, so let's determine whether or not this matrix has an inverse, and if so, what that inverse is. The most efficient way to do this is to first augment the matrix with the identity matrix on the right-hand side of an augmentation bar. Then, row reduce this augmented matrix completely until the left-hand side becomes the identity matrix. The goal is to get the left-hand side of this augmented matrix to be a 1 on every diagonal entry and a 0 everywhere else. We'll implement that process with this example, and in doing so discover that this matrix A that began on the left-hand side of the augment bar can indeed, through a series of elementary row operations, be row reduced until it becomes the identity matrix. That also means that in the process, what began as an identity matrix on the right side of this augment bar has now turned into a new matrix, and that new matrix is the inverse, A inverse. So this row reduction has discovered for us the inverse of the matrix A. Now if we wish to use that inverse matrix to solve this equation in particular, all we need to do is use that inverse to cancel the original matrix A from the left-hand side. To do that, we need to multiply by A inverse on the left-hand side of both sides of this equation, so that it reads A inverse times AX on the left and A inverse times B on the right. When we simplify that arithmetic, the matrix multiplication which is happening on the left side of the equal sign, A inverse times A, by definition of invertibility, if we computed the inverse correctly, that matrix multiplication should come out to equal the identity matrix. And this is helpful because the identity matrix, multiplied by any matrix or vector on either side, has the property that it leaves that matrix or vector as itself. I times x is equal to x. And therefore we have successfully canceled the matrix A from the left side of this equation. Then what remains on the right-hand side must therefore be the solution. X equals this vector on the right-hand side. All we need to do then is carry out the necessary matrix vector product to determine A inverse times B. Multiplying the first row of A by the column B and the second row of A by the column B, we discover in this example that x is equal to the vector -7, 13. So we can use the inverse of a matrix, when it exists, to solve the equation AX equals B. We first need to discover that inverse matrix, for which the simplest way is usually to apply row reduction to the augmented matrix that begins with the identity matrix on the right. When our row reduction succeeds in moving the identity matrix to the left side of the augment bar, then what remains on the right at the end of that process is the inverse of A. We can then multiply by that inverse on the left of both sides of the equation to cancel the original matrix A and leave x by itself, and the right-hand side is then the unique solution of this system.